Okay, welcome everybody. My name is Dr. Eric Woodroof. I'm happy to be here, and today we're going to be talking about a very, very short webinar. It's not that short. It's about an hour long, but we're going to be covering what is net present value, and this is very important in the financial world. And so this whole webinar is going to be about how to take energy projects and translate them into a language that financial people generally speak. And so net present value, once again, my name is Eric Woodroof. That's my picture. This is my company. It's called Profitable Green Solutions. We do a fair amount of consulting and training all over the world. Many continents, many different clients, have an opportunity to work with a lot of fun people. I happen to be the president of the Association of Energy Engineers this year. And I'm also the chairman of the board of the Carbon Program and a board member since 1989 of the Energy CEM program. So do this kind of live talk all the time. And actually the slides you're going to be seeing are directly from the CEM class. So this is going to be kind of a preview of really, a very, very short sample of what you would see in the CEM class in the economics section, which is a very important piece of that whole class. So agenda, this is very, very simple. We're just going to show you why is this important, how to calculate net present value, and maybe a few other things, and then we will conclude. This will be about 25 slides, probably take about an hour, but hopefully you'll find it interesting and engaging. Again, these are slides directly from the Association of Energy Engineers, and this is from the CEM program, and this is the section we call Economic Analysis and Life Cycle Costing. Now, why do we even bother with this? Let me just say that money, obviously money today is worth more than if you got the same amount of money 10 years from now, because theoretically you can invest that money, and if if the stockbroker was doing well or the stock market was doing well, your money would grow. But just, that's a theoretical thing. So anyway, money today is worth more than it is future. And the other problem with energy projects is generally most people use simple payback, which is a very easy evaluation tool to show the benefits of a project, but it doesn't really give the whole picture. And I'd like to demonstrate that right here. This is I can use some tools here for you. This is an example of two projects here. You've got, on the left-hand column going down the page, you've got basically years, end of year 1, end of year 2, end of year 3, 4, 5, 6, etc. And then let's say you have two projects, and let's say your project is project A, okay? And basically your project, you'd invest $100,000 today, and you would get back $45,000 after year 1, $45,000 after year 2. In savings, you get $45,000 for many years to come. And that's pretty typical of an energy project, say a lighting project or some very, very quick payback project. Now let's say, you're presenting this project to a CFO, and you're obviously going to be competing because you're always competing for money, basically. And you might be competing against another project, Project B over here. And Project B, just coincidentally, also is a $100,000 investment. And by the way, I should have noted this a little better. I should say minus $100,000 in this first two columns here. First row. Anyway, so you got minus $100,000, and then you'd get $50,000 back the first year, $50,000. But let's say Project B only lasts for 3 years. Well, that's great. And if you were to evaluate this on simple payback, unfortunately, you would lose because Project B, your competing project, the CFO only has so much money to fund, and he's got to put his 100K somewhere. He's going to go with Project B if you use simple payback, because this one's going to pay back in 2 years, and this one's going to pay back in a little over 2 years. And the whole problem with simple payback is basically if you were to draw a line wherever the first project meets the simple payback, in this case Project B has a 2-year simple payback. In 2 years you've recovered your money. The problem with that is that it doesn't calculate, simple payback does not include all the value that's down here for both of these projects. The evaluation ends whenever the first project meets its simple payback. And so that's not really fair because you're missing out, your project misses out on all this value here, this 45K times 4 years, and their project misses out a little too. So simple payback doesn't give you the whole picture. And there's a little more to this story. I mean, really, in truth, if you wanted to evaluate this, academically accurate, you would have to make these projects of equal lives, or maybe you'd make do Project B twice or something. But essentially, life isn't fair, and projects get presented, and it's your job to present your project in the most accurate and favorable way. And if you do simple payback, you're going to be missing out on a lot of the value. And so that's really the motivation behind this, is we want to give the energy engineer the tools to calculate this information so that you can present your energy project, and you should win. We want you to win and get more projects implemented, save more energy, save more carbon, all the other good environmental benefits that go with that, save more money for one. And so that's really why we're doing this whole webinar. So anyway, that's kind of a short overview of this process and why we're messing around with simple payback. Again, I had said that basically it's all about calculating that money and moving it back to an evaluation period called net present value. And really, that whole exercise is about moving money through time. And so the rest of this seminar, we're basically going to be talking about how do you move money through time. Okay, so here's let's just say a different project. Say you've got a project that saves $5,000 per year. Here's what we would call a cash flow diagram. You just kind of work with me on these graphics here. These are pretty primitive. This is end of year 0, and time is going out this direction on the x-axis. And so end of year 1, end of year 2, end of year 3, end of year 4, end of year 5, etc. And let's say this project would last for 6 years. So n would be 6. We should draw a 6 right there. The n is 6. And basically this project lasts for 6 years. It saves $5,000 a year. This is what the cash flow diagram would look like. Is we would have basically, $5,000 savings here, $5,000 savings here, $5,000 savings here, etc., etc. That is kind of what is going on in this scenario for 6 years. Okay, and just for now, the object of this, the thing we're trying to do here, is to take these savings cash flows right here, and we want to move them back in time to figure out what would they be worth in an imaginary, what I would call present value. What is the value of that today? And this really isn't a cash flow, but we want to know how much, if we had a cash flow here at time 0, if we got all this money, 5K, 5K, 5K out in time, what would it be worth if we moved all that money back today? Because like I said before, going back one slide, I'm sorry, we're not going back money through one slide, we're going forward one slide. When we get money out in the future, if we get $10,000 out in the future, it's really not worth $10,000 to us, because we have to discount the money and figure out what it would be worth today. In other words, looking at this in a more simple, maybe something you're more familiar with, if you had $6,200, okay, today, you could put that in the bank and it would grow. And it would grow, and then in 5 years it would be worth $10,000, okay? Just say if you didn't take any money out. So therefore, if money grows going forward in time, we have to discount it when we're going back in time, okay? So we got $10,000, we get it one time out in the future, but we can't get it until 5 years, so what is it worth today? That's what we call discounting. And so really, going back to this slide, it's all about moving money through time. It's all about taking these cash flows that are happening out in the future and moving them back in time. And this is a terrible arrow, and I'm sorry about that. We'll try to make this casual, but I'll try to do a reasonable job with professional drawings. Anyway, we're trying to move this money back in time to figure out what is it worth today. If someone says, I'm going to give you $5,000 the next 6 years, what is it worth to me now? If I had all that money now, what would it be worth? And so that's what net present value is. That's what we're going to be trying to do. And we'll be given a couple other bits of information like the interest rate to discount it at, etc. So that's ultimately the objective, is to move money that we get in the future back to time 0, back to the present. And that's part of the process of calculating net present value. Okay, so that's kind of the overall game plan of this. There's a couple of terms you need to know, and let me go through those. First term is something called an annuity, and that's a term used to describe an equal cash flow that's happening every single year. So basically the savings of any project, energy project, say you're going to save $5,000 or $10,000 a year, if it's the same every year, that we call that an annuity. Okay, we're getting the same amount of money every year. And so that's what an annuity is. Depreciation is more of a complex term. We really cover that better in the class. For here, I'll just say that depreciation is the book value loss of an asset year to year. So, if you've ever bought a boat or an RV, you definitely understand depreciation. But basically, on an accountant's definition, it's like if you buy a asset that's $100,000, and it's supposed to last 5 years. That means at the end of 5 years, it's worthless. To the accountant, that's the way they think. And so you would depreciate that thing. If it's going to be 5 years long and it's $100,000 value, you would depreciate it basically 1/5 of the value every year. So you depreciate, 1/5 of 100,000 is $20,000, and you depreciate that every single year. So at the end of the first year, you bought the thing for 100. At the end of the first year, it's really only worth 80 now. At the end, and the end of the second year, it's only worth 60. In the end of the third year, it's worth 40, and et cetera. And so that's what depreciation is. It's not a cash flow, but depreciation helps you because it allows you to basically, it allows you to reduce your taxable income. We'll cover more about that later. It's something that helps you basically reduce taxes. Now, another term you'll hear is something called future value. That's a one-time cash flow you get way out in the future. Say you've got, an inheritance would be a good one, or say you've got a project that has a salvage value or a disposal cost. You're going to have a one-time either payment or one-time revenue that's going to happen sometime out in the future, but just once. Then you'd call that a future value. And then internal rate of return is another evaluation method, much like net present value, uses very similar type discounting technology. But basically, internal rate of return is another way that people evaluate projects. Now, net present value is probably the most classically accurate, but IRR is another one that's used often. Now, another term you'll see often is something called minimum attractive rate of return, and every one of you has a minimum attractive rate of return. It can be expressed as a hurdle rate. It can be expressed as a certain percentage. If you're looking for, if you expect to get 10% because that's what your portfolio will get, then you're not going to be interested in projects that have less than a 10% return because you can get that 10% pretty solidly somewhere else. So minimum attractive rate of return is something that every company has in its personality and every person has in its personality. And some of the examples we do in the class, excuse me, is we say that, everyone is willing to take action when you meet a certain hurdle rate. For some of you, if I said I have, $1,000 to give you if you can, crawl on your hands and knees for 100 yards, that might get someone to take action. But if I said it was just $2, maybe it's not enough. Maybe it's not an incentive for you to take action. So everyone has one of these, and we have a saying. I've written papers. If you go to Profitable Green Solutions, you can find papers that we've talked about. Many people are more motivated to take action when they're avoiding pain than they are seeking pleasure. If I said, like I said, if it was $2, it may make it a little more realistic. Say it was $10 to crawl on your hands and knees, you'd probably, might not be so excited to do it. But if I said, if you don't do it, you're going to pay me that $10, then more of you likely would take action. So anyway, hurdle rate is something that minimum attractive rate of return, basically the same thing. Or some people say we're not going to entertain anything with less than a 2-year simple payback. That's another way of saying that's our hurdle rate, 50% return, basically. And so every company has one, and we have to know what that is. If we don't know what the minimum attractive rate of return, we are wasting our time because that's like going on a Valentine's date and not knowing what's going to satisfy the person you're taking out. So if you've ever done that before, you won't make that mistake again. So you have to know what the target is before you start doing projects. So minimum attractive rate of return, very important to know. And again, that's dictated by the company, whereas before I was talking about internal rate of return, that is going to be related to a project. So MARR, minimum attractive rate of return, is related to the company. Just need to remember that. Net present value, that's ultimately what we're trying to find here is what the net present value, that is our evaluation tool. If I get so much money out in the future and the project costs so much today, what is the net gain to me in today's dollars, basically? What is the net present value? And so that's what we're trying to do. And if you're looking at projects and the NPV is 0, that means the project adds 0 value to you today, and so you really wouldn't be motivated to do something that's going to only give you 0 value. If the project's NPV is negative, you probably don't want to do the project because if you do the project, you're basically throwing money out the window. Unless you have to do it, you have to have a water system or something like that. So if net present value is positive, that's a good thing, and the more positive it is, usually the better it is. Okay, so you want your projects to have lots of net present value. The project with the biggest NPV over the same time frame is the one that you're going to want to choose. Now, to get NPV, it's actually a multi-step process. It's really a two-step process, and we'll go through that. Basically, there's one of the many steps there is called present value, and we need to figure out what the present value of projects in their cash flows are, and I'll show you how to do that in a few minutes. Probably the most common term that you guys have heard of already is something called simple payback, which basically is, the most common evaluation tool out there. Simple payback is basically a very simple algebraic manipulation where you say, if a project costs $100,000 to start and the savings are $22,000, you would take the $100,000, put it in the numerator, divide by $22,000, and that would tell you how many years. Roughly, in rough numbers, this is slightly less than 5 years because we know that 100,000 divided by 22 is a little less than 5. And so, excuse me, I went forward a little too quickly there. So basically, simple payback is pretty common for most facility managers, and you may have to present that as well. But if you want to sell to the higher level people in the organization, if you get into, carbon emissions and all these other things, or if you're just trying to present your energy projects in a little bit more of a higher value proposition, you might use net present value because you're actually calculating that value and showing a more holistic view of your project, which is good. So another thing I mentioned before, salvage value could be a one-time cash flow, etc. We'll skip that for now. Let me give you, going back to our sample here, we've got a project that saves $5,000 per year, and just kind of demonstrating how we're going to apply these terms, here's the cash flow diagram. Excuse me, I've got this cough and it's still bothering me a little bit. So anyway, say we got a project $5,000, here's the cash flow diagram. We've got basically $5,000, $5,000, $5,000, et cetera, et cetera, et cetera. It goes for 6 years, and we're given that this thing has a 15% interest rate, meaning that means that the company says, hey, we can do your project, or we can take the money and invest it somewhere else and get 15%. So whatever your project is, we're going to discount the future cash flows at 15% because that's exactly what we could get if we just took that money and put it elsewhere. So we take that discount rate from the company, and we're just going to call that I as 15%. The savings is $5,000 per year. We want to find what is the present value of this cash flow diagram. We're doing this first step of figuring out what the net present value is. Now, and this will make sense as we go through this, but for now, just think, what is the present value of the savings cash flow stream is what we're trying to do. Now, there's a couple of terms we have to know to be able to convert this money. We're basically taking all this money here. Let me go to my highlighter pen again. Where's my highlighter thing? Sorry, I'm a little couple technical. It's not a major difficulty. I guess we can get by pointer options. There it is. So there we go. So basically, we're trying to move all this money here that's happening in the future, move it back to time right now to figure out what is this imaginary present value of the savings cash flows. What would that arrow look like if we could move all of this money back in time? And so basically, to move that money through time, we have to transform it. We have to basically go to some tables, or you can do it on a calculator, but it's basically an algebraic manipulation. And this is a terminology that's pretty common in the marketplace that people talk about. It's all about this right here, pain. I'm sorry, I'm having some pointer issues. It's all about pain, and I don't mean the kind of pain you get when you work out. But basically, they have this formulation, this notation that's basically about, if you want to know, there's always 4 variables, and you'll always be given 3. What you want to know will be on the left side of the slash here. This is the slash. What you want to know is the present value, that's the P, and what you're given is these other variables, which is AIN. Now, A is the savings cash flow because that's the same every year, $5,000, $5,000, $5,000, etc. I was 15%, and N is the number of payments. In this case, it was 6 years, right? The thing lasts for 6 years. That's what we're going to be using as the number of payments, and we're just assuming that you get 1 payment per year on that deal. So if you've got AIN right here, we can say that's what we've got, and we want to know P. We would use this notation. It's called pain. And then you would have to go to these things called tables, which I think are in the next slide. Yeah, basically we're going to go to tables. So let's convert some of our cash flow diagram first. We have P is over here. That's what we want to know. We want to know what is the present value of these savings cash flows occurring out in time. We have A, which is our savings. A is 5,000, and I is 15%. We just rewrite the problem in this cash flow diagram so we can see it in the way that the notation is going to allow us to solve the problem. Okay, so we always want to go, what are we trying to find? This time we're trying to find present value of given AIN. And so we go to these tables, and the first thing I'll tell you about the tables is that this is just one option to do this. If you have a calculator that can do this for you, fantastic. Many mortgage people, people real estate industry, they have these financial calculators that you punch 4 buttons and you're done. But if you don't have that, you can do this with tables, and this will actually help you if you do it through the tables by understanding it a little bit better. First thing I'll tell you about tables is don't worry about this side over here. We're not going to mess around with gradient series. We're only focusing on probably the central 4 columns today, just to keep things simple. And basically this is called uniform series, so that means anything that has a same cash flow every year. That's what we call uniform, and series means that you're getting it every year. So these are the different notations. You'll notice FAs and PAs. The notation we talked about earlier is we want to find P given AIN, which is this almost central column here. Remember, we were up here. We want to find P given AIN. So going back to the table, P given AIN, we take a look at, this is the column we want to focus on. And this tells us, up in the upper left-hand corner, it tells us our interest rate that we're operating with, and I believe that our interest rate on the previous slide was 15%, so we're going to go to the 15% table. If you had 20%, you go to a different table. N is on the left-hand side going down, so basically our P given A, it was 6 years. We come over here at 6 years. Our factor is going to be 3.7845. Now, most of the time you're just going to go to 2 significant digits, but let's just say it's 3.78. 3.78. We'll stick with that, or close to it. Doesn't really matter. But that's our factor. Now, once we find this factor, there's something you have to remember is we're going to these tables. Okay, overall objective again is to move the money back in time, the $5K per year, move that back in time to figure out what it's worth today. Next step is to go find this table factor, and we're going to take this table factor, whatever it is we find, and we're going to multiply by the money that's moving through time. Now, in this case, the money that was moving through time is $5,000. We want to move $5,000 through time. We go to the table, we get the right factor, and we multiply that factor by the money that's moving through time. And our factor was 3.7845. So if we take basically, what is the the present value of the savings cash flows, we would take our $5,000, that's the money we're moving through time, which is the A, okay? We multiply by the table factor, which this is the pain formula, find P given AIN, I is 15 and a 6, go to the table, get this factor, and it's 3.7845. Multiply that out, and it tells us our present value, this imaginary thing that we have over here, is now, we know what it is, and it's going to be, this P is going to be $18,922. Now that's really the first major step in figuring out what the net present value. And the problem with this project is that, yes, we are going to save this money, absolutely, and it's going to be worth, today in today's dollars, the savings is worth $18,922. That's great, we've done that, but that's not the whole story. The whole story has to involve that we've had to invest some money to start the project, right? So we have some installation costs. So we have to take, what is this P value over here? What is this positive or savings cash flow? What does this arrow look like? Which we just figured out is $18,922. We have to compare that against, this value here, the cost of the project, right? And once we take the difference between those two, that tells us the net present value. So if the project, let's say it costs $10,000, if the project costs $10,000, one-time payment up front, and because that payment happens at time 0, we don't have to move it anywhere. We can leave it right where it is. We don't have to discount it. We don't have to move it. There's no transformation. So $10,000 directly in the time 0, and I write the arrows going down, but you can do it as long as it's opposite. As long as the cost is opposite of the savings 0, you're fine. But since it's going down at $10,000 right here, we got $18,000 going up in present value of the savings cash flow. So you take 18,000 minus 10, and your net, notice the word net present value, is $8,922. That means that overall, this project is worth $8,922 if we got the money today. If we, this whole project is basically like saying we're putting, you would tell your boss, hey, do this project. It's like putting $8,922 in the bank today. Okay, and that's basically how you would present the project, because that is the net present value. It calculates the present value of the savings, takes off the cost, and that's what's left over, and that's what we call it net. And so if this was going through fast, you can always repeat and replay this webinar, which is kind of nice. But I'm just going to keep going at this pace, so if you need to back up and go back over some things, that's fine. It's all there for you, and if you need to read more, there's papers on PG at Profitable Green Solutions, which will tell you more about the theory, and there's a lot more stuff to this if you want to get into it. But we're doing the quick and dirty version, and this is basically the net sum game we're trying to get to. Is we were asked, what is the net present value of a $5,000 project over 6 years at 15% interest? We figured out the present value of the savings cash flow, and then we did the cost part of that, and the net present value is $8,922. Let's take another example. Let's say one that would involve a different transformation, but let's say you win the lottery. And hey, if you win the lottery, you're probably going to stop listening to this webinar. But hypothetically, if you won the lottery, you could be offered $100,000 today, or they might give you an option. They might say take $100,000 today, or they might say, well, or we'll pay you a certain amount of money at the end of every year for the next 10 years. And if you just ignore taxes for now, how much would that amount of money have to be? How much would X have to be for you to choose the option? And say, you're pretty happy with your investments, you're getting 15% elsewhere, so that's your minimum attractive rate of return. In that case, basically what you've got going on is you're going to be having to figure out a slightly different cash flow model. In this case, this time we are finding A given P, I, and N. Okay, and this time we're trying to find the A. What is the equivalent amount of money I could get every year given my present value, my I, and my N? Okay, and so we draw the cash flow diagram this way. We could take $100,000 right now, which would be at time 0, or we could spread that money out over time, not take the $100,000. What would the amount of cash flow look like each year, equivalent amount each year, and given that at 10 years the payments would stop? So notice notice this is kind of notation. They do these ... to mean this continues on until 10 years. So if I had more space, I would draw 10 arrows and keep going like this, but we just draw ... and 10 means we're going to 10 years. So notice the notation is different, but the methodology is very similar. We have basically what is the money we're moving through time? That's $100,000. We have that multiplied some table factor that we need to go find. The table factor notation is find A given PIN. So we basically need to go find that. Now, do we have everything we need? We've got I, check. We've got N, check. We have P, check. So we're going to go to the tables. We're going to find that, and I thought I had the tables in there. We'll have to go back. Well, I'm going to scroll down to find this is the problem when you do a live seminar. You never know if you got everything right. So what percent? 15% interest, so we could just go back to the previous table. We'll go back to this table. The N was 10 years, so 15%, 10 years. Now this column we're going to look for this time is find A given P. It's this column. Again, uniform series. We know P, we know I, we know N. We're trying to find A, so we come down to year 10, and the factor is 1993. Hopefully everyone sees that. You can basically take that factor, multiply by that by the money that's moving through time, which in this case is $100,000. So you got $100,000 times 1993, which basically comes out to be that this A is going to equal $19,000, or roughly $20,000, and that's what you're going to get every year for 10 years. So you have to. So if you were to tell that to your fifth grader, hey, I can take $20,000 for 10 years, they would add up the math and say, Daddy, that's $200,000. Well, that is true, but because we have to discount that money, getting $200,000 spread out over 10 years is the same as getting $100,000 today at the 15% interest rate. Okay, so just kind of different ways to think about it. So that's what you would you could either take $100,000 or you could take $19,930 every year for the next 10 years. It'd be equivalent because all we're doing is we're spreading this money out over time. It's the same process. We're just going about it in the reverse direction. Instead of moving money that's in the future, moving it back in time. This time we're taking what is a lump sum given right now. What would it be worth if we spread it out over time? Same exact process. So if you can do these kinds of things, this is basically the math and how to do net present value. There's a lot more to this, and you can get far deeper in doing internal rate of return calculations and other stuff. I don't want to cram too much into a webinar because people start to lose their attention. But essentially, you would, whatever you're doing, you would draw a diagram of your cash flow situation. Try to map it out the way I've shown you. And it doesn't really matter how your notation is. I personally like to draw positive arrows as savings and negative as arrows down, but you can draw them whatever way you want. As long as the arrow for savings is opposite of the arrow for costs, you're going to be fine. And draw out your diagram, figure out what kind of notation you're looking for, go get the table factor and multiply by the money through time, and that's how you figure out the present value of a cash flow. And then once you get those all back to zero, you do the net present value calculation and you're done. So that's that. I skipped that slide. Let me give you a couple other examples. And this one's kind of a little bit of a twist. And again, I'm going fast because the webinar you can always pause and go backwards. But I want to keep moving because we're doing pretty good at this pace here. So here's an example of a project, say a boiler economizer. You don't have to know even what a boiler economizer is, but let's say it costs $20,000. So you're going to spend $20,000 up front, and you want to know how much will it have to save every year if the life is 5 years to return 12%. So you're given this MARR is 12%. You're given 5 years. Now in this case, we know what the cost is. We know, and I'm going to draw on the screen here. We know this thing, and I draw it. Well, I guess we know that this thing is going to cost $20,000. We should think in our heads right now, well, that thing, whatever it costs, it better have a present value of savings that is bigger than the present value of the cost. If the present value of the cost is $20,000, this thing better darn well have a net present value that's more than $1. So this thing better save more than $20,000 even after we move all that money back in time to the present value. So if the cost is $20,000, this thing better have a present value of the savings cash flows of more than $20,000. So let's just say, just for simplicity, just to set it at zero, let's say that the present value of the positive cash flows, we say, okay, we know that's got to be $20,000. What would happen if we spread this out over time? Okay, how much would it have to save every year to deliver $20,000? Because that's really the target. We know it has to deliver that, and now we have our notation. We have what we need. We have a money here. We want to move this money out over time. We go to the same basic notation we've been talking about. Basically, this is a find A given P, find the annuity, find the savings that's happening every year given P, I, and N. We draw it, we go to the tables, we find out what this factor is. Again, this is a 5-year project, so we could go back to those tables, and I encourage you could do that, I guess. I don't know, maybe I should do it for you. Let's see, what was the percent? It was 12%, so I got to give you a 12% table. So 12% up here, we would come down, it's a 5-year project. This is find A given P is 2774. Let's see if that was the right thing. Yep, 27441 is our table factor. Multiplied by the money we're moving through time is 20K. We know this thing had better save $5,548 every year, or we're not doing the project. So that's the criteria. And if the boiler economizer salesperson comes to you and says, "Hey, this thing's going to save $4,000 a year," you're going to tell them, "No, it's not good enough. If we're going to invest 20 grand, it's going to have to save $5,500, or we're not interested." And so you can use this as a negotiation tool too, because it really is, you cannot sell this to upper management unless it meets this criteria, and this tells you what that criteria is in an annual cash flow basis. And so basically that's another example. If you pause the slide, you can look through this one and do it. It's basically the same as the one we did earlier, but these are just very classic examples of how to do this kind of stuff. Excuse me. Now, a couple of benefits, limitations, net present value. It does, like I said, take into consideration the time value of money. It takes into consideration, the project in terms of dollars. It's not a year thing. It gives you dollars. It basically moves future cash flows back to the time zero, et cetera, et cetera. There's a lot of benefits to it. Limitations, it doesn't really work very well when you compare projects of different lifespans. If you've got a project that's 5 years versus 10, technically this is not going to give you the most accurate answer. So you try to make the lifespans equal, or you can do something called annual worth, which is another process. And again, we have that in papers if you want to go there. But or annual value, that's another little step you can do, and then you can compare. So those are the things you can do. But most of the time, it's going to be pretty neat. Now, a couple areas. Some of you are probably working in private corporations or have clients that are private corporations, and you might have to deal with after-tax cash flows, because that is really what a company uses to invest in projects. Is after they pay taxes, they have money left over, then they can reinvest in projects for the next year. And so a lot of companies choose to use after-tax cash flows because that's maybe a little more realistic. And let me show you how to do this. This weaves into the depreciation discussion. So say this is the example up here. You've got basically some device, waste heat recovery device, that will last 5 years. So right now that oops, I'm already giving away the farm there. I'm telling you what, we're almost near the end. That'll probably make some of you very happy. So this thing's going to last 5 years. We know that. That's our N right there. It's going to cost $100,000. That's our investment. It's not really our P, but that's our investment. We know it's going to cost $100,000. So in my head, I'm thinking I'm drawing a cash flow diagram with $100,000 times 0 going in one direction or another. And we know it's going to save $30,000 per year. Now, I'm going to ask you to think on yourself, what does that mean, saving $30,000 every year? That sounds a lot like an annuity to me. Okay. Now, this is the before taxes aspect of it. If the salvage value is 0, means the thing has no value at the end of life, what is the after-tax cash flow if we're paying 25% taxes? Now, this example is assuming that your company is profitable. If your company is making money, okay, then you're paying taxes. And if you save any money, if you do any reduction in cost, basically that's going to mean you're going to make more profit, which means you're going to be taxed more. And so that's what the tenets of this example are based on. So let's take a look. First thing, let me orientate you to the table, and I apologize, this isn't, maybe I can fix it really quick. Let's see if I can fix it. Okay, hopefully I can fix this. And, sorry, this is, it's never as fast as you imagine it. But this particular chart needs to come down, so we can do this really quick. Okay, so let's go back to... okay, so I think I'm back online. That was kind of strange. Anyway, let's just check that. Yeah, we're showing, we're recording, everything's good. So I fixed the table. Let's take a look at this in a way we can see it. And bam, we're back online here. Okay, so basically, if we set this problem up and you have years going down the page this way, and these are basically processes you're going to have to do to find the after-tax cash flow. So let's just walk through this slowly. At end of year 0, or year 0, you invest $100,000 in this project. Okay, and basically you invest $100,000. Your after-tax cash flow is you spent $100,000. Congratulations. That's the easiest part of this problem. Okay, so you just spent $100,000, bam, out the door. Next year, first year, you save $30,000, and then the year after that, 30, 30, 30. You can see this is basically your annuity right here. But if we're going to get to after-tax cash flow, we have to adjust that a little bit. And adjusting it involves taking into account the depreciation, which is basically going to reduce our taxable income. Let me show you how. Depreciation per year. If this thing is $100,000 and it lasts 5 years, I showed you that before, that basically the depreciation is going to be $20,000 a year. Okay, so at the end of the first year, the thing loses 20% of its book value. And basically we take, what the cool thing about depreciation is, it allows us to take that out of the savings cash flow. So savings is 30. That's like saying our profit's going to be $30,000 more next year, but because depreciation is 20, we're only paying taxable income on 10. 30 minus 20 is $10,000. And so that's what we have to pay taxes on. We pay taxes at $2,500 because this is a 25% tax rate. This is 25% times 10,000 is $2,500. So that's our taxes. Now, this particular column here, I'm not really that psyched about, column number 5. Let's just kind of X this out for now and just ignore this. The simple way to calculate after-tax cash flow is take the before-tax cash flow, which is $30,000, subtract off what you pay in taxes, which is $2,500. So $30,000 minus $2,500 gives you $27,500. Okay, we'll make an equal sign. And so basically, $30,000 minus $2,500 is $27,500. That is our after-tax cash flow. That is really the after-tax benefit we get out of this every year. Now, this is, you're going to get this at the end of year 1, this at the end of year 2, year 3, year 4. This column now here becomes our annuity, and we run the same kind of process we showed earlier. It's just instead of showing arrows up at $30,000, we're going to be showing arrows at 27.5, and then we basically, that's our annuity. We go for 5 years, we go to the tables, we find our table factor, we multiply the table factor by the money that's moved through time, which in this case would be 27.5. Pull that back to find out what the present value of the savings cash flows, which would be 27.5. We compare that against our cost, and then we have net present value. That's how you would do this type of problem, and I'm just kind of showing you how to do it. Some of you might have to do it, some of you might not. But this kind of overview of basic net present value calculations, I've tried to do this very quickly for you. Hopefully you got some value out of it. Hopefully it helps some of you. I'm sure it'll help some of you be able to sell more projects, which is ultimately where I want to go. I want you guys to be able to do more, sell more, get more projects implemented, because that's what it's all about. If you don't save any energy, we're not helping anything. And so hopefully this information, if you need to rewind it, review it, go over it a few times, that's fine. What we just covered is a pretty significant part of an entire semester of college engineering, engineering economics. And so we've gone through it very, very quickly in a very condensed format. And so I hope you've enjoyed it. Hopefully you get a lot out of it. If you have any questions, you can always call me. I think we have our information there is at the front. Let's see if I can get back there. Still new computer, new keys. You can find me at this phone number or go to profitablegreensolutions.com and you can get the information you need. But I've enjoyed being with you today. Hopefully this helps you. And with that, I will stop the recording, and I wish you all the best, and go save some energy. Take care.